next presentation is from Helen Monkhouse. Hi, Helen. Helen is a commercial manager of functional safety at Hariba Myra with over 20 years experience in the automotive industry. Helen promotes industry best practice through her work with MISRA, ISO 26262 and ACE groups. And as if that wasn't enough, you're currently a part-time PhD student as well at the University of York. So, my goodness, well done.
I suppose just picking up on the point that I'm currently a part-time PhD student at the University of York as well. I suppose I should say that in this presentation, part of it has been kind of reflecting on where we are within the industry in terms of functional safety and bringing in greater automation into the industry. And also I thought I'd kind of embrace the academic side of me, and it probably raises more questions than it has solutions. So what I really want to talk about, I'll go through some of this early part quite quickly because I think many of the other speakers have touched upon it. But it's kind of the backdrop to what we mean by automotive safety, and also what I'm going to call the functional safety paradigm. And then basically look at that and say, well, how is that paradigm affected with greater automation? And also I'll touch upon some work that's being done on safety of the intended functionality. Then try and sort of couple that into what we're here for today, to look at verification and validation. And finally, my summary is just some where I see the challenges. So if we think about safety, many people think about automotive safety in terms of either passive safety systems where you're really trying to reduce the severity of an accident. So I'm thinking of things here like airbag systems, restraint systems, for example. Then kind of more recently, we've seen the introduction of active safety systems, so things like ABS and stability control, which really are around supporting the driver in preventing those critical situations like a skid on an icy road, for example, becoming an accident. And then more recently, we're getting into the advanced driver assistance systems where we're saying, okay, we try and maintain the vehicle in a safe situation, so we don't put the vehicle and its passengers into a situation that becomes critical in the first place. And if we think about this kind of flow of technologies, then clearly they all have a functional safety aspect to them, because if they go wrong, then they can cause hazards. But I think the other thing to kind of view with this is, as we kind of move from sort of across the screen, then we start to see that those systems are also far more complex and have far more authority over the vehicle control itself. I'll go quite quickly through this slide. It's a timeline of kind of functional safety through the ages, as it were. A couple of key things to point out really is the fact that although ISO 26262 edition 1 came out in 2011, really a lot of the work and a lot of the underlying principles probably came back in the sort of early 1990s. So although, as Edith's already said, the second edition of the standard comes out, it's planned for 2018, that's still based on principles back here. And you could say, well, moving forwards with increased autonomy, okay, we might be looking at edition 3 of the standard, you know, sort of mid 2020s maybe. But even then, is that really going to support some of the challenges we've got? So I almost feel that we're trying to solve 21st century problems with a set of principles that were defined in the 20th century. And kind of looking at that, there's something that I've called the functional safety paradigm. which I think is the principles really that underlines the way we approach functional safety within the automotive industry at the moment. So, as has already been said, we kind of assume that we're applying the standard to single features, which the ISO standard calls the item. So very much this idea of you've got some inputs, you've got a control system and a set of actuators on that. And we kind of tend to view the hazards that one of those systems can cause coming from failures within the system. So we very much look at it as sort of a box where we draw a boundary around the box and kind of open the lid to say, well, okay, what are the faults that can occur with this and how can they cause hazards? As we've already touched upon as well, I think kind of where functional safety has come from in the automotive industry is assumed that the driver is always in the loop as well, where clearly as we start bringing in more assistance systems and autopilot systems, then we take the driver out of the loop for all or part of the mission. And then finally, we have this kind of idea of fail silent. So you kind of say, well, okay, if I've got a problem, if I detect a fault within my system, then I'll shut the system down or at least degrade the functionality. So if that's the kind of paradigm of where we are, that we're sort of saying, well, I'll put a boundary around my system, I'll look inside it to look at what faults can lead to hazards. I'll assume that if I do have a problem, I'll shut the system down or even reduce the functionality such that the driver is able to maintain control. How does greater automation kind of fly in the face of that paradigm? So if we think first of all about how we would approach the safety of a system like this initially, this could be the sort of chain of functions that you would need to perhaps control a vehicle at the moment. And so we'd say, well, today in manual driving, the driver would be doing the perception, reasoning and demand parts of this control, and the vehicle itself would be doing the control and actuation. So as I said before, we'd draw the boundary around the control, and so we'd have something like this diagram where we'd be analysing the bit inside the blue dotted box. So if this was sort of an engine controller, for example, we might say, well, okay, the demand is the accelerator pedal position. The control is taking in a bunch of other inputs from around the vehicle, and that's coming out as an engine torque demand. And we might think about, well, what are the hazard causes? And you might say, well, okay, we could have a failure of control that would lead to an incorrect engine torque. We'd look at the severity of the hazard, which we could define as undemanded acceleration, and we could define a safety goal that says, well, okay, avoid undemanded acceleration. And in order to achieve that, we might say, well, if we detect a failure, then we'd apply a torque clamp. So we've defined a level of integrity. I've just picked an arbitrary ASIL B here. So we could decide to develop that whole control system to ASIL B, to a high integrity level. But more commonly, we'd say, well, okay, rather than trying to define the whole complex system to a high level of integrity, we'll use a monitor, which is an example like this you can do. And kind of from a safety engineer's perspective, I always think, the acronym KISS, keep it simple, stupid. So which you can kind of apply to this, because you can say, well, okay, I've got a fairly simple set of monitoring functions there, which I can define well. I can probably get close to 100% test coverage of that little monitoring function. And in this case as well, the safe state for the monitor is quite obvious as well, that we can shut the system down with a torque clamp. And so that's quite nice to specify and verify. But if we then think, well, if we add autonomy to this, then really we're saying that maybe this whole bit is the vehicle, is under vehicle control. And if we maybe ignore the control and the actuation part of saying, well, that's what we do today, if we just sort of concentrate on the new bit and put the item boundary around that, we kind of start to have a system that looks something like this, which we would then try and apply the functional safety standard to. If we started to put some of the potential inputs on this, then we're kind of looking at a perception function that's probably taking in sort of camera, LiDAR data, a plethora of other sensory systems from around the vehicle. And it's probably using neural networks, data fusion, other AI principles to actually model the environment in order that the reasoning function can decide where other vehicles are, where pedestrians are, what the road layout is, etc. So if this was still functions that related to vehicle motion demand, if we started saying, well, what are the hazards associated with this, then it's okay, is unsafe acceleration. If we were talking about vehicle motion demand, we'd kind of have to set the integrity level all the way up at ASIL D, because we're taking the driver out of the loop, so we can't take any credit for any controllability that they may be able to provide. We've clearly got a safety goal of avoid unsafe acceleration, but really what's the safe state? I mean, maybe if our function is a valet parking function, it's okay to shut the system down, but clearly if we're on lane 3 of the motorway, then that's not going to be a clever outcome. Also, if we start thinking about hazard causes, well, a fault within that flow could lead to a hazard, but equally it could be external factors, and probably more likely to be external factors within the environment that actually leads to the vehicle motion demand being unsafe. And this kind of realization is one of the reasons for a publicly available standard being developed called Safety of the Intended Function, and that's currently being developed as part of the ISO 26262 group, but it's unclear at the moment whether this will become a separate standard or a part of ISO 26262. There's kind of two schools of thought, and I think it will be over the course of time will determine which way the ISO standard goes. So really, this is just a flow chart from the standard, which comes with the usual caveat that this is a very draft standard at the moment. So don't take anything I tell you as gospel as far as this is concerned, because it could change. But really, area 1, which is the sort of top grey area here, is all about making sure you get the function right. So this really comes to the sort of systems engineering aspects of it again, of being able to ensure that you have the right function in the first place. Then area 2 is around looking at again the function working in its known use cases and saying, well, is it robust, or how do we need to change the function so we don't get false positives and incorrect system behavior. And then the last area, I think, is around, they term it evaluation of unknown use cases, which always kind of feels a bit weird to me, but it's trying to say, well, once you've done all of this stuff, how much confidence have you got that when you put the system, free the system out into the wild, it won't experience a situation where you get unsafe behavior. So how does this all affect verification and validation? Well, if we sort of quickly skip through and think about how we would perhaps build a safety case for a system today, and then look at the impact of the safety of the intended functionality. Now, I just want to put up a model here, which comes from some work that we're doing within MISRA under the safety case guidelines, and it's really breaking down evidence into different types of evidence which we can use to reason around the safety of a system. So the first is the rationale, which says, well, what confidence have I got that my requirements are right in the first place? The second set of evidence is around satisfaction. So how do I know that my system has really implemented the requirements as stated? Then there's a means argument, which is about the processes we use. And finally, I think perhaps the weakest evidence is more about the environment. So saying that the culture in which, or the safety culture of the organisation in which the product's developed. So if we think about those kind of types of evidence for our current sort of systems today, then, as I was saying, particularly if we're using a monitoring function, we can define the safety mechanisms quite precisely, and they're very deterministic. So you think in terms of, well, to validate those requirements, I can do fault injection testing, and that can really provide me with evidence that yes, my monitoring function is able to detect failures in control. And verification, I haven't used the systems engineering V, but I'm referring to it, in terms of, you can think of verification of requirements all through that systems engineering V, and coming out with the evidence needed to demonstrate safety. But when we then start thinking about, well, how would I do the same thing for my intended function, then it becomes more difficult, because we then have to start building evidence that says, well, I'm confident that the function is operating correctly and interacting with its environment correctly. And verification targets perhaps aren't pass-fail anymore. It's we're getting into shades of grey of when is something operating correctly and when isn't it. And the validation targets that we might need, we might have to build up from accident statistic data and require greater sort of scenario simulation. And for area 2, it's then being able to verify the correctness of the sensors and actuators operating in their environment, particularly if for changing weather conditions or reflections from reflections that give sensors false positives, for example. And also being able to verify these functions within the system, that the perception function is really correctly modeling its environment, and based on that model, that the reasoning function is actually making correct decisions. And then the challenge for area 3 really is that, as I was just saying, the perception function is correctly modeling its environment, and an overall sort of confidence regarding the robustness. So I'd really to summarise, highly automated systems are clearly breaking the current functional safety paradigm. Verification in the future, I think, is going to change and need to be much more statistically based rather than sort of perhaps the pass-fail criteria we use at the moment. And I think that certainly needs greater support in the tool chain in terms of tools and simulation tools to support the verification and validation of these kind of systems. That just leaves me to say thank you very much for listening, and any questions? Yeah, the question was, is kind of what does an unsafe behaviour look like, or how do we define that moving forwards? And I think you're right. It becomes incredibly difficult because, I mean, I think I've viewed it here from very much an engineering perspective that says, well, okay, if we can write it down, how would we go about verifying or validating it? But really, what you're touching upon there, I think, is some of the subtler issues of, well, are we, introducing these systems to reduce a risk in other areas, and is there a balance between? And to be honest, I don't know what the answer is between, the balance between putting systems in that potentially reduce the risks to car users, but equally they might be creating their own risk as well. So yeah, I think it's going to be a real challenge over the next sort of 20 years to see how that starts to play out, really.
Thank you.